Namaste everyone. Welcome to second PUC physics class. We were discussing about the response of AC by different components. Response to AC. So namaste everyone. We have discussed the response of resistor to an AC circuit. In an AC circuit, or the response of resistor to AC. How does alternating current and voltage vary in a purely resistive circuit? And we know that in a purely resistive circuit, current and voltages are in phase. When current reaches the highest value, voltage also reaches its highest value. When current reaches zero, voltage is also zero. When current reaches negative maximum, voltage also changes its polarity and it becomes negative highest. So they are in phase. The phase difference between them is zero. So it can be proved in an equation like this. So you have to consider a resistor connected to an AC like this. So consider an AC circuit containing a pure resistor of resistance R connected to an AC source of alternating EMF V is equal to Vm sin omega t. So let me connect a resistor. Okay, I will connect it like this. Resistor, and here is an AC source, and V is equal to Vm sin omega t is the alternating EMF applied, equation 1. And you know that in V is equal to Vm sin omega t, V is the instantaneous value of EMF, Vm is the peak value of EMF, and that is NAB omega, and omega is the angular frequency, right? So we will write it now. V is the instantaneous value of EMF, instantaneous value of EMF, and Vm is the peak value of EMF, and omega is equal to 2 pi nu is the angular frequency. Okay, now when you apply the voltage like this, what about the current in the circuit? If you want to know what is the current, I is equal to V by R, that is V is nothing but the sinusoidally varying current. It doesn't change, it doesn't remain the same always. Vm sin omega t by R, and now if you club this, Vm by R, when the voltage is in the peak position, if you divide it by the resistance, you should get the peak current, right? Vm by R gives the peak value of current, and I is equal to Im sin omega t. This is equation 2. Equations 1 and 2 show that, okay, equations 1 and 2 show that, right, I and V are in phase. So how do you show this graphically and in terms of Phasor diagram and wave diagram? You have to show it. So equations 1 and 2 show that current is in phase with the voltage, and Im is the peak value of current which is obtained by Vm by R. So after this substitution, we get it like this. So there is no phase difference between current and voltage, because voltage equation and current equations, they contain identical sin omega t. There is no change in the omega t plus phi, minus phi, something like that we don't have. So they are in identical phase. So how do you show this in wave diagram? It is like this. So later on we have to show it in Phasor diagram, and here is the voltage that is selected, because the voltage starts from 0. It is V is equal to Vm sin omega t. When omega t is 0, V is 0. What about current? Current also starts from 0, because it also contains I is equal to Im sin omega t. So they are in phase. When one is at highest position, another is also at highest position. When one is at 0, another is at 0, negative highest. So this corresponds to I and this corresponds to V. So this is V. Okay, right, yeah, this is V and this is I. Okay, now so here we draw V or I, voltage or current, and this is omega t phase, of course, for this one. Now if you select a particular phase at a particular instant, how will be the current and voltages in the circuit? And if you connect an ammeter and a voltmeter across the resistor, both should be able to measure alternating current and alternating voltage. If you connect it in the circuit, you will find that at an instant of time, corresponding to the current, you will get a suitable voltage. When the current reaches highest, the suitable value of voltage also reaches to highest value. When the current reaches 0, the voltage also reaches to 0. So suppose you select some omega t phase like this. Suppose this is omega t1, some angle. At that moment, how will be the current and how will be the voltage? So this is the position of current here in the Phasor diagram, and this is voltage here at this instant. So like this. Now if you want to represent both, this is the phasor for voltage, right, and this is the phasor for current. Where is the green? It is here. This is the phasor for current, like this. So this is I and this is V. Of course I have to indicate the current, this angle, phasor angle. This is omega t1. So it starts turning, that vector starts turning from 0 to some other value. Right, that is how we indicate it. So this diagram is very important. Hope you have followed it. At a particular instant of time, at a particular angle omega t, at a particular phase angle of the coil or AC, if you find it out how is the voltage and how is the current, then you will get the phasor diagram. Up to this it is the current, and up to this it is the voltage, and both the phase angle, both the vectors, both the phasors are showing the same phase angle omega t. Okay, now in a purely resistive circuit, current and voltages are in phase. That means when the current is highest, voltage is also highest. When the current is 0, voltage is also 0. They are like very good friends. They don't change their phase at all. Now do you have a circuit? In the previous class we were discussing about that. Do you have a circuit where when current is maximum, voltage is 0. When voltage is maximum, current is 0. When voltage is minus maximum, current is 0. Something like that. Do you have any circuit? That is capacitive circuit. So take a capacitive circuit. Now connect a capacitor across an AC source. So consider an AC source, connect it across a capacitor. Okay, capacitor means, you know, it is a system used to store charges, and it contains two parallel metal plates separated by a dielectric medium, and it is used to store charges. Yeah, these are the two plates of a capacitor C, and the supplied EMF is alternating Vm sin omega t. So consider an alternating EMF V is equal to Vm sin omega t applied to a pure capacitor of capacitance C as shown in the figure, like this. You connect it like this. Now before analyzing this circuit, now let us see how does it respond. How does a capacitor respond in DC? The same effect can be applied here also. How does a capacitor respond to DC? It is very simple, like this. Suppose you take a capacitor, connect it to a battery and switch it on, and you connect an ammeter. This analysis is very important. Once you understand this analysis, the derivation of this is nothing for you. So this is capacitor, and you connect a voltmeter like this. Now okay, we will study the polarity plus minus and plus minus. Switch on the circuit. When you switch on the battery, battery will start doing the work. What type of work? Battery will have, but you see, capacitor is made up of two metal plates, and both the metal plates will be rich in free electrons, because metals have plenty of free electrons. So this battery has a potential difference, and it can do the work. It will extract electrons from plate A, say, and those electrons will be sent to plate B. So battery will do work in sending the electrons from plate A to plate B. Suppose the first electron is taken from plate A to plate B. Since A has lost one electron, and it gets positively charged, and since B has gained one electron, it gets positively charged. And this work is done by the battery in sending the charge from one plate to another. So negative charge is taken to the plate B, because minus will repel the electrons, plus will attract the electrons. So electrons are attracted from the positive potential, and negative potential will repel them. So one electron is lost from plate A, and one electron is gained by plate B. Plate A is positively charged, B is negatively charged. There is a potential difference now. Now you can see that there is a voltage in across the capacitor, because there is a potential difference. This is at higher potential, this is at lower potential, there is a difference. Now allow the battery to do work further. Battery won't keep quiet. it will start extracting electrons from plate A continuously. So second electron is transferred from plate A to plate B. So this is negatively charged, this is positively charged. But you ask the battery, how was the situation when you were taking the first electron from plate A to plate B? Battery says, no problem, nobody was resisting, and I have taken the first electron from plate A to plate B very easily. What about second electron? Sir, when I took the second electron from plate A to plate B, it became very difficult because already arrived electron started opposing me. So the work done in sending the second electron will be little bit more. So, but battery will have enough energy, so it will send the second electron. Similarly, the third electron. Battery says, sir, third electron, it is very difficult to send the third electron from plate A to plate B, and the fourth electron. As the electrons are transferred from plate A to plate B, battery finds it more and more difficult to send the electrons because already accumulated electrons will oppose. That means already developed potential difference will oppose the motion of electrons from one plate to another. So battery has to do the work in against this opposition. Battery has to do the work against this opposition in sending the electrons from one plate to another. So battery will keep on sending the electrons. Now the thing is, just see the voltmeter reading. You just imagine how will be the voltmeter reading. In the beginning, battery will be energetic. Of course, battery will be energetic always. And no electrons will be found in plate B. So battery finds it easy to send the electrons to plate B. In the beginning, opposition is less. As more and more electrons get accumulated in the plate B, battery finds it difficult to send the electrons. So flow of electrons from one plate to another plate goes on decreasing as the time passes. In the sense, current goes on decreasing as the time passes. In the beginning, current will be highest. What do you mean by current? First of all, it is the rate of flow of charges. Now, what do you mean by rate of flow of charges? The amount of charge that is flown from one plate to another plate, or the amount of charge that is flowing in the circuit, that depends on how many electrons have flown. Because one electron makes 1.602 into 10 to the power minus 19 coulombs. What about 10 electrons? 1.16 into 10 to the power minus 19 coulomb. 100 electrons, 160, 1000 electrons, 1600. In the beginning, more and more electrons will be flowing, means more and more amount of charge is flowing per second. As the time passes, battery finds it difficult to send the electrons from plate A to plate B. The amount of charge flowing from plate A to plate B goes on decreasing. That means current keeps on decreasing. That means ammeter in the beginning will be showing the highest reading, and as the time passes, its reading goes on decreasing. So ammeter is in a position showing a reading from maximum to 0. It is decreasing from maximum to 0. It is cos theta. Did you understand it? Because cos theta, in the beginning itself, cos 0, 1, and it decreases to 0 after 90 degrees. Cos 90 is 0. What about voltmeter reading? Voltmeter reading in the beginning will be 0. Why? Because unless the capacitor is charged, we won't have potential difference. If you want to have potential difference, you have to produce a difference in the potential by charging the two plates. In the beginning, charge in the two plates is 0. As one electron gets transferred from plate A to plate B, little bit of charge is developed. There is a potential difference. As the electrons accumulate in the plate B, the potential difference goes on increasing, and the potential difference is shown by that voltmeter. So how will be the voltmeter reading as you switch it on? As soon as you switch it on, voltmeter reading will be 0, and once you switch it on, electrons get transferred from plate A to plate B, and the voltage starts increasing from 0 to maximum. Once the battery, as its capacity, as according to its capacity, sends a fixed amount of electrons from plate A to plate B, what happens is all the accumulated electrons here in the plate B effectively oppose the arrival of the next electron. That means battery will face a stage where it cannot bring further electrons. So movement of electrons stops. Does it mean that battery has no energy? No, it has got energy, but that energy will not be sufficient to send the next electron because already accumulated electrons will oppose. So that situation will arise, and we say that the capacitor has charged. We say that capacitor is completely charged. Now, suppose this is a 5 volt battery, then this will also be 5 volt. That means capacitor has done work according to its capacity. Right? Battery has done work according to its energy. and it has transferred all its potential difference here. Of course, it has transferred all its energy to here. So capacitor gets charged to a potential which is almost equal to the potential of the battery. So almost equal, but a small amount of potential. Suppose this is 5 volt, this may be 4.9, practically it may be 4.95, 4.98, because some energy is wasted in the form of heat while transferring the electrons. So that much energy of battery will not be found here. Okay, so potential difference will decrease little bit. But let us take theoretically that this is same. Now that means this voltmeter, as soon as when you are switching on, voltmeter was showing 0 reading. As you switch it on, voltmeter starts more and more reading, because more and more electrons will accumulate, potential difference will increase. That is shown by the voltmeter. What about ammeter? In the beginning, activity of electrons is more. Battery will be sending more and more electrons from plate A to plate B. It will be throwing away because it will have less opposition at the plate B. But once the capacitor is completely charged, battery will not be able to send further electrons to plate B. Flow of electrons stops. That means current stops. Right? So current becomes 0, voltage becomes maximum. It's exactly similar to the values of sin theta, cos theta. Sin 0 starts from 0, right? Cos 0, highest itself, 1. Sin 45 degree, 1 by root 2. Cos 45 degree, 1 by root 2, 0.707. Sin 90, 1. Cos 90, 0. So voltage equation should have sin theta, because it starts from 0 to 1. 0 to maximum, whereas current equation should contain cos theta, because it falls from maximum to 0. This is the exact circuit where current and voltages are having a phase difference of 90 degree. That is the meaning. Once you understand this meaning, derivation is nothing. You can understand it in any way, right? So this is the gist of the story that is coming in a capacitive circuit. So in a capacitive circuit, current and voltages are having a phase difference of 90 degree. Now again a question comes, who leads? Who is leading? When owner and dog are going for a walk, who is leading? Dog is leading. Dog goes first and then the owner, right? So who is leading? Current is leading. Why? As soon as you switch it on, who is in the highest position? That is current. Voltage will be starting to raise, right? It starts from 0. As it starts from 0 and goes to the maximum, the current reduces to 0, and then voltage comes to 0. Now if you just replace this by an AC source, replace this by an AC source, instead of connecting a DC, connect an AC. What happens to AC? AC rises, becomes 0, minus maximum 0, like this. So if it happens so, capacitor charges, goes to the highest voltage, becomes 0 and goes to the negative maximum. By that time current also changes, but current doesn't change along with voltage. It shows a ulta case, right? It is not like in a resistor. In a resistor both are in phase, but in a capacitor they are not in phase. They have a phase difference of 90 degrees. Okay, so how will be the equations then? If V is equal to Vm sin omega t, then I must be is equal to Im cos omega t, because I should lead. I think you have followed this. Current should lead. What do you mean by current leading? As soon as you switch it on, current will be in the highest position itself. It has already gone to +1, and this voltage is starting to rise and this decreases. So we will see. So in a purely capacitive circuit, remember, current leads the voltage by a phase angle of pi by 2. You see this sentence and the sentence and the reality, or in the experimental fact, you have to combine them. You must know the meaning of that. We write only one sentence, that is, in a purely capacitive AC circuit, current leads the voltage by pi by 2. Just quote this sentence and try to understand what is the meaning of the sentence. In a purely capacitive AC circuit, current leads the voltage by pi by 2. The meaning is, if you have a capacitor and an AC source connected to the pure capacitor, what happens is, as soon as you switch it on, current will be highest and voltage will be 0. As voltage increases, that means as the capacitor gets completely charged, current drops to 0, and current leads the voltage, because at the beginning itself it is highest, and both of them will not be found maximum or 0 together. Okay, we will have an equation for it, and you know that we must get an equation I is equal to Im cos omega t, right? We will see how to get it. Now First of all, we will write the equation for charge across the stored in the capacitor. What do you mean by charge stored in the capacitor? Remember CV Raman, right? Charge stored in the capacitor is CV. Now as you switch it on, you know that this equation or this diagram, I need it again. So battery and as you switch it on, one by one electron is transferred, and the one which loses electron gets positively charged, one which gains electron gets negatively charged. As the capacitor gets charged, what happens is charge stored in the capacitor goes on increasing. And if you want to know what is the charge stored in the capacitor, here Q plus Q and minus Q, magnitude of Q, then you will find that you should have the capacitance of the capacitor, which is a constant, and the voltage across the capacitor. What is the voltage across the capacitor at that instant, and the capacitance of the capacitor, Q equal to CV. I usually say to remember this by CV Raman. Okay, Q equal to CV. Now, but V is not a constant voltage, it is a timely varying alternating voltage. Q is equal to C. What is V? Vm sin omega t. So from here you have to start. Why did you write the equation for Q, sir? We want to compare voltage with current. Then why did you write the equation for Q? Of course, if you want to get the equation for current, equation for charge will help you. You know that current is equal to dq by dt. You know this fact, right? It is a rate of flow of charges. So once you get the equation for charge, you can differentiate it and you can get the value of current. And now we know that the current equation should have cos omega t or sin omega t plus pi by 2. Sin omega t plus 90. It should be leaning by 90 degrees. Okay, how to get it now? So we got the equation for charge. Charge Q equal to CV, where V is equal to Vm sin omega t. Now, what is current? Current is equal to dq by dt, that is d by dt of CVm sin omega t. Correct? Because charge across the capacitor at any moment is equal to capacitance of the capacitor and voltage across the capacitor at any moment. That is instantaneous voltage. Instantaneous voltage is given by V is equal to Vm sin omega t. So now once you get this, differentiate this and you will get current. What is I is equal to? Shall I differentiate? I is equal to, okay, I want a new chalk, d by dt of CVm sin omega t. You know that CVm, it is a constant. Capacitance of the capacitor doesn't change. It depends on the dimensions of the capacitor, the size, area and all. And what about the thing which is varying is time. This is variable time. So I have to differentiate CVm d by dt of sin omega t. That's all. It is the one which changes the value of alternating voltage. Okay, I'll rub this. Now differentiate it again. I is equal to CVm constant, d by dt of sin omega t, d by dt of sin d by d theta of sin theta is cos theta into differentiation of theta also, because here you have omega t, right? Cos omega t into differentiation of omega t, omega, because d by dt of omega t, see, d by dt of sin omega t is differentiation of sin omega t is cos omega t into differentiation of omega t is omega, because d by, here omega is a constant, d by dt of t. When I differentiate this omega t, you have to differentiate omega and t, but the differentiation of omega is a constant, you can take it out, and differentiation of t is 1. So cos omega t into omega. So what do you have now? I is equal to Vm omega c. I'll bring this here and I'll write it together. Vm omega c cos omega t. Okay. Now you say, of course, cos omega t can be written as sin omega t plus pi by 2. Sin omega t plus pi by 2. Okay. Now you see, if you come back here to the resistive circuit, what did you do in the resistive circuit here? Now here we did it like this. In order to get the value of current, we divided voltage to the resistance value, V by R, because current is, this is simple Ohm's law, but V is Vm sin omega t by R. What is Vm by R? Vm, the voltage, peak value of voltage divided by resistance was taken as peak value of current. Now can you do something like this here? Peak value of voltage divided by some resistance. Sir, where is resistance here? Here is only capacitance. But capacitor is an instrument used to store energy or to store charges. But capacitor opposes the flow of charges, and it also opposes the flow of AC and alternating current, and it will have a resistance to AC, and that resistance to AC is called reactance of the capacitor. Resistance given by the capacitor to the flow of alternating current is called reactance, and its symbol is Xc, and its unit is ohm itself. Okay, yes, these are all the different things. Resistance given by a capacitor to the flow of AC is called reactance. We don't call it as resistance, because resistance is the resistance of a metal to the flow of DC, or even AC, no problem. Resistance is the resistance of any metal. But a capacitor also offers resistance to the flow of AC, and that is called reactance, another name, and it is represented as Xc, and its unit is ohm. And if you want to get the reactance of a capacitor, that means opposition given by the capacitor to the flow of AC, I want to have Vm divided by some reactance. That is, I will write it like this, Vm by 1 by omega c. I will write it like this, because you know that 1 by x is equal to x itself, right? So this omega c will come to the numerator, sine omega t plus pi by 2. I is equal to Vm divided by, if I want to have the same type of relation, Vm by R, here it is a pure resistor, whereas here it is not a pure resistor, it is a capacitor. I will indicate this as its reactance Xc. What is its reactance? Opposition given by the capacitor to the flow of AC. And I will call this term as Xc sine omega t plus pi by 2. You know that sine 90 plus theta is cos theta. Now I is equal to Vm by reactance, peak value of voltage divided by reactance of the capacitor, and that is called Im. I can treat this as Im sine omega t plus pi by 2. Okay, this is equation 2. Now compare these two equations. V is equal to Vm sine omega t is the first equation. Voltage was taken to be like this. So voltage varies sinusoidally like this. I is equal to Im sine omega t plus pi by 2. You compare these two equations. Here you have an extra pi by 2. So what does it indicate? In a purely capacitive circuit, current leads the voltage by pi by 2. So shall I write that sentence? In a purely capacitive AC circuit, current leads voltage by pi by 2. Hope you have understood the meaning of this. And current leads, I leads. Why? Because as soon as you switch on, current will be in the one position, highest position, voltage 0. Then voltage increases and current decreases. So that is the meaning of this. So here we have sine omega t plus pi by 2, that is nothing but cos omega t, which is leading sine omega t. Cos omega t always leads, sine omega t follows. Okay, sine theta follows. Okay, so this is how you can prove. Now we analyze what is this Xc. What is Xc, sir? Xc is called reactance of the capacitor. Okay, shall I rub somewhere and get this? I think I can rub this. Okay, little bit here. Okay, yeah. Xc is called reactance of the capacitor. Now from where you will get the equation for Xc? You see, Im is substituted as Vm by Xc, correct? The peak value of current is taken as, in the derivation, we assumed it. Peak value of current is the peak value of voltage divided by reactance of the capacitor. Vm divided by Xc. So that implies, what is Xc? It is Vm by Im. Correct? It is the peak value of voltage divided by peak value of current. As if we have voltage by current as the resistance of a wire, right? V by, you bring this here, V by I is equal to R, isn't it? Resistance. Whatever it is, whether it is DC voltage or AC voltage, DC current or AC current, voltage by current is equal to resistance. This voltage by this current, that is the peak value of voltage across the capacitor, divided by the peak value of current through the capacitor is called reactance of the capacitor. Now I do one thing. Sir, do you need to have only peak value of voltage and peak value of current in order to find out the reactance of the capacitor? This is simple like Ohm's law. No, you need not. Divide this by root 2. Divide this by root 2. What you will get? Peak value of voltage by root 2, RMS value. Peak value of current by root 2, RMS value. So what you will get? This is equal to Vrms by Irms. This is also the reactance of the capacitor. Right? So how do you find out the reactance of capacitor? Pass an AC, then find out the peak value of voltage, peak value of current. Divide them. RMS value of voltage to the RMS value of current. Get the ratio. That is the reactance of the capacitor, and it is also measured in ohm. Also, you see here, if you come here, Vm by Xc is taken as Im, right? And Xc is the replacement for 1 by omega c. Can you see that? So reactance of a capacitor is given by 1 by omega c. That is equal to 1 by 2 pi nu, because omega is 2 pi nu. Omega is theta by t, that is 2 pi by t, and so it is 1 by 2 pi nu c. Now you see this equation. If you are asked to define what is capacitive reactance, you can define it like this. Capacitive reactance is the ratio of RMS voltage across the capacitor to the RMS value of current through it. Capacitive reactance is the ratio of peak value of current, peak value of voltage across the capacitor to the peak value of current through it. Capacitive reactance is 1 by omega c or 1 by 2 pi nu c. Now here is a surprising thing. What is that? That is capacitive, you see, resistance, voltage by current is called resistance. It is the peak value of voltage to the peak value of current, or RMS to RMS. That is resistance. Now, does resistance have any other formula depending on omega? No. Resistance of a resistor does not depend on the frequency of AC. Whatever the AC signal you have connected, whatever the DC signal you have connected, resistance of a resistor is independent of the source across which you have connected it. For example, if you have a 100 ohm resistor, what is its resistance when it is connected to 10 volt battery? It's a very, very awkward question, isn't it? Resistance of a resistor is 100 ohm. If it is connected to a 10 volt battery, what is its resistance? It is 100 ohm, because resistance of a resistor or a metal depends only on its dimensions and its nature and its structure. It doesn't depend on the source. So even if you connect 100 ohm resistor to a 10 volt battery or a 5 volt battery or a 6 volt battery or a 500 volt AC source or 500 volt DC source, whatever it is, its resistance remains constant. It doesn't depend on the battery across which it is connected. So that's why we had R equal to V by I formula only. So whatever the voltage that you get across the resistor divided by current through the resistor, that gives the resistance of the resistor. Whereas here you see reactance of a capacitor, it is depending on the frequency of AC, nu, whatever the AC is connected. Reactance of a capacitor is not a quantity which is independent of the source across which it is connected. It depends on the frequency of AC that is connected across it. So reactance of a capacitor may be the peak value of voltage by peak value of current or RMS voltage by RMS current, but it depends on the frequency of AC. Means a capacitor gives different reactances for different sources of different alternating sources. So capacitor gives different reactances to different alternating sources. Of course, right. So we will analyze it again later. Now before that, of course we can do that now. One thing, suppose you connect a capacitor to a DC battery, and just now I will rub this so that I will get enough space to analyze it. Okay, so connect a capacitor to a DC source. Now what the result we have got? A switch and a capacitor here. What the result we have got? Once the capacitor is switched on and it was allowed to charge for a sufficient amount of time, finally we got the result like this. Capacitor charged, and okay, after once all the electrons were shifted from here to here, that means according to the capacity according to the ability of the battery, once this is completely positively charged and this is also V volt, this capacitor, the charging process stops. That means all the electrons, according to the ability of the battery, if all the electrons have moved from plate A to plate B, flow of electrons stops. Ammeter current becomes 0 and this voltage will be highest, correct? Now what about the circuit? It's a dead circuit. No current flows to the circuit. No current flows to the capacitor or battery. Capacitor is fully charged. Current in the circuit is 0. Now you ask the capacitor or ask the battery, how much opposition is shown by the capacitor to you, battery? Battery, how much opposition is shown by the capacitor now? Battery says, sir, capacitor is not allowing even a single bit of charge to move. Current is 0, sir. That means how much should be the resistance of the capacitor, reactance of the capacitor? It should be infinity, correct? Am I right? Resistance given by the capacitor, what you call reactance, to the DC source is infinity. What do you mean by that? Once the capacitor is connected to a DC source, you will get current in the circuit only when the capacitor is charging. Of course, you know that the current is highest in the beginning because the flow of charges is very highest. In the beginning, battery finds it easy to send the electrons to plate B, other plate, because the opposition is less. As the time passes, it becomes very difficult for the battery to send electrons to the other plate because the accumulated electrons oppose, so current starts reducing. Once enough amount of electrons are sent from one plate to another, battery finds it a situation that it cannot send the further electrons. Flow of electrons stops, current becomes 0. If in a circuit current is 0, what is the resistance? Infinity. It is like an open circuit. So once the capacitor is completely charged, it is like an open circuit. Resistance or the reactance given by the capacitor is infinity. So capacitor, we say capacitor blocks DC. Sir, what is the meaning of this? Capacitor blocks DC. Very simple. Take this one. Xc is equal to 1 by 2 pi nu c. Now what is the frequency of a DC? An AC source has a frequency. What about the frequency of DC? Does DC change its direction every now and then? No. What is the time in, how many number of times the DC changes the direction in 1 second? No time. 0. Frequency of DC is 0. 1 by 0, that is infinite. So you can prove it here, right? So you can understand it how a capacitor blocks DC. What do you mean by that? You must know the meaning properly, because if you connect a capacitor to any DC source, capacitor allows the current to flow through in the DC circuit only for a certain amount of time till it gets completely charged. Once the capacitor completely gets charged, there is no flow of electrons, and the flow of electrons stops, and the resistance given by the capacitor, what you call reactance, is infinity. And you can prove it in the formula also. X is equal to 1 by 2 pi nu c. Nu is the frequency of AC, and if it is 0, frequency of DC, now since we are discussing DC, frequency of DC is 0, X is infinity. Okay, now we have to draw a phasor diagram for both. It's like this. Yeah, shall we write it here? Yes. Phasor diagram and vector diagram. Yeah, it is like this. Shall I draw it here? And can you, oh, this wire, can I see it here? Yeah. Yes, you have to draw a diagram showing the variation of current and voltages. Yes. Do you need so much space actually? No. We need not go to that much extent. Yes. Here. Yeah. Now, this is voltage. Because voltage starts from 0. No, you can't see that. I have to bring this side. Right? Yes. Voltage starts from 0. It is V is equal to Vm sin omega t. Right? When you put 0 here, you get 0. Whereas current, where is the current equation? I have rubbed it. I is equal to Im sin omega t plus pi by 2. You know this. When you put omega t is equal to 0, then this is sine 90, that is 1. So when voltage starts from 0, current will start decreasing from maximum to 0. You know this. So this is maximum and this is 0, this is minus maximum, this is 0, and here is plus maximum. So current will be going like this. You must be very careful while drawing this. You shouldn't draw as you want, right? When this is 0, voltage is 0, current is highest. You know that. In the beginning, current is highest. Activity of electrons is more. Electrons will be flowing very easily because there is no opposition. As the time passes, flow of electrons reduces, current reduces, but voltage builds up. When voltage is highest, current is 0. When current reaches minus highest, voltage reaches 0. When voltage reaches minus highest, current is 0. So can I name this as I and this as V, and this is voltage or current V or I, and this is omega t phase. Now cut the graph at a particular value of omega t. Say somewhere here, at some value of voltage and current, omega t1. Find out the corresponding values of voltage and current here. Right? So like this. How will be the voltage and current? If you represent voltage and current in a Phasor diagram, that means vector notation, then you know that current leads and voltage lags. So how will be the current? Current should be leading. So this purple color represents current here. So current should be leading. That means current should be here. This is I. Sorry, I have to represent it by purple color. And voltage, white one. Voltage should be here. Hope you have followed this one, right? This is V. Last time they were together because current and voltages were in phase. Current and voltages were in phase means when the current is highest, voltage is also highest. When current is 0, voltage is also 0. But now when current is leading, current is highest, voltage is 0. So when voltage is highest, current is 0. They have a phase difference of 90 degrees, and that difference is nothing but this one. This is 90 degree phase difference, this angle, and this is omega t1, that is at some instant. At whatever instant, they should be at 90 degree only. So they should keep that 90 degree difference always, the two vectors. Right? This may be any value, but as they move, they will keep that 90 degree difference always. Because you see, when this is at 0, as highest, this is at 0. When this comes to 0, minus highest. So that 90 degree phase difference is always maintained. Whether you are 16 years of age or whether 20 years of age, your brother will always be 2 years elder, right? Elder. If you and your brother are having a phase difference, age difference of 2 years, that 2 years is maintained always. How much you get aged, whatever be the age, that 2 years difference will be maintained. Similarly here, that omega t1 is maintained. So that's how we indicate it. Hope you have followed this Phasor diagram, right? So they were together here. Now current has moved forward by 90 degrees. Earlier they were in phase 0. Now it has moved forward by 90 degrees, and omega t1 is the instant at which, the phase instant at which we have seen the condition. So it is like this. But this diagram is very important. This should also look like a sine wave, and you should be very careful. This is 0 minus maximum, 0 minus maximum, 0 plus maximum. It should be very proper. Hope you have followed this. So for the time being, I will stop it. We will have one more circuit, that is inductive circuit. We will compare it, how a current and voltages are related that. So we are moving forward in this AC circuit. So study this. If you have any questions, please message to me, or you can have a voice call, or you can call me at after 7 p.m. I will answer it. Thank you for watching my class. We will have more discussion in the coming classes. Thank you.